So this is where we left off. We were talking about organic compounds, we were talking about prefixes, and we were learning a new language of organic chemistry. And I told you that in this next video, we're going to have to go through and talk about this term called isomer. Now, this is not isotope. Isotope is something that you have learned about in general chemistry, maybe. Isomer is something completely different. Mer in organic chemistry represents unit. And iso means same. Think of isosceles triangle. Iso starts isosceles triangle off. An isosceles triangle, by definition, is what? A triangle that has two equal sides. All right, a very symmetrical triangle here. Well, an isomer in organic is a structural unit that has something that's the same. What does that mean? Okay, well, let's go and take a look at butane. This is kind of the first time that it happens. So butane has 4 carbons, and I draw the hydrogens on it to make it look happy. I want all of these things happy. I want them to like me, so I have to make sure that I do my job the right way. There we go. And we said this is butane. 4 carbons in a row. 1, 2, 3, 4. All of them have single bonds all the way around. And all of those single bonds means that it's an alkane, which means it ends in ane. But if someone really wanted to be smart alecky, and I'm not going to even call it smart alecky because they're pretty smart if they decide to do this, they could say, well, whoa, wait a minute. Why did you draw all of the carbons in a straight line? Why can't you do this? 1, 2, 3, and have the 4th come down here? Do we have to go in a straight line all the time? And the answer is no, we don't. This is where some of the problems come in with organic, because we don't have to go into a straight line. We can have these little vergences that happen. Well, it still requires 4 bonds. Hydrogens, hydrogens, hydrogens. Here's our 4th one. Here is a hydrogen and a hydrogen and a hydrogen. And then this one down here needs a hydrogen, a hydrogen, and a hydrogen. This makes all of them have 4 all the way around. So if I count the number of carbons up here, 1, 2, 3, 4. And if I count the number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And then if I do the same thing down here, how many carbons? 1, 2, 3, 4. And then how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you see the word the same comes from. It's the same number of carbons and the same number of hydrogens. Folks, it's the same numbers of all the atoms. If this was not a hydrocarbon, and I had oxygens in here and nitrogens and phosphoruses and so forth, if it has the same number of every atom, and they're identical when it comes to this, then this is what we call an isomer. It is an option. Another option for you to choose. Sometimes we need to use the 4 carbons that are in a row. Sometimes we don't. Sometimes we need to use the carbons that are down here, 3 in a row with 1 poking out. But both of these have the same number of carbons and the same number of hydrogens, which is what we call an isomer. That is different than an isotope, okay? An isotope means a skinny little molecule or atom and a fat little molecule or atom. Okay, isotope means there's a different mass number. The mass number changes. One's skinny, one's fat. Isomer has nothing to do with mass. An isomer has everything to do with the same numbers of each atoms, but they are connected in a different way. You have a choice, and that choice is how they are connected. That is the definition of an isomer. Now, if we want it to be really, really proper, anytime there's a choice on how to link the carbons up like we've done here in this case, well, we do call it an isomer, but the proper term is a constitutional isomer. So isomers, two or more chemical substances, like we've drawn here, having the same composition, which basically means the same number of atoms, and molecular weight. If they have the same number of atoms, well, if you did the formula weight for this thing and you did the formula weight for this one, you would get the same number here as well. They only differ in structure. That's it. So, as you can imagine, the bigger the molecules that we're going to get, the more choices we have to draw them. And the more choices means more options, which means more names, and that complicates things up quite a bit for us, right? So this is called butane, and this structure, it's not called butane, okay? Butane can only represent one structure, and that's it. So butane, it represents a 4-carbon straight chain molecule. Butane only represents this one. That's it, folks, no more. This one actually has a different name that it goes by. So we're going to have to learn how to name these isomers whenever we have them. Well, there's a short-handed way to name the isomers, and there's a long-handed way to name the isomers. And quite honestly, people prefer the long way better than the short way. But not in the case of butane. This is the only option that we can have for butane. All right? We cannot draw this anymore. This is a 3-carbon chain, right? 1, 2, 3. There we go. There's a 3-carbon chain with a carbon hanging off. Well, that's the only option that you have for butane. And because of that, we can simply call this isobutane, because it represents the isomer of butane. Again, a PhD made that call. Well, what I like to tell people in the world with ISO units, whenever you see ISO, what I like for you to think about is this structure of an L shape that's happening right here. Right, you see that? That's like an upside down L. Carbon, carbon, whoop, goes down, carbon. That structure of an L is going to be the ISO unit. So this is ISO, and then you count the total number of carbons up. 1, 2, 3, and 4. So 4 in total. So isobutane is going to be that name. So now you're thinking, well, wait a minute. There's actually more than one way to draw that. You know, here you did 1, 2, 3, and 4. I'm going to leave the hydrogens off. And then you did a 1, 2, 3, and then you popped one down here below. Well, what if I do like 1, 2, and 1 up above and 1 below? What about that one? That's a different way. No, it's not. It's not. And you're probably scratching your head and say, well, why? Because this one is that same structure up here. It's just turned on its side. Do you see that? I can take this structure and I can just turn it, and then I have the same structure down here below. Another way that you could determine this is figure out the longest, what we call carbon chain. The longest carbon chain here is 3. It's all the way across. 1, 2, 3, whoop. And then here we've got 1 hanging down. So 1 off to the side. Well, what's your longest carbon chain here? Well, your longest carbon chain here is going to be here. 1, 2, 3. There you go. And 1's hanging off to the side, and that's in the middle. And this one that was hanging off to the side, that's in the middle too. So these two are the same structure. They're equal. They're no different. There's no way, no other option that you can draw this butane other than your first choice and your second choice here. You can try to get a little crafty or creative, and you can draw these in weird kind of positions, but it's the same type of structure. There is no difference. So because of that, that is also isobutane. There is no difference there. So we can draw pentane. Let's draw pentane. All right? So pentane, pent is 5. 1, 2, 3, 4, 5. I'm going to leave off the hydrogens. If you want to put them on there, you can, but I'm going to start making this a little bit shorter and quicker for us. So understand the hydrogens are there. And then question number 2 might say, draw the structure of isopentane. Okay, well, one of the reasons I'm leaving off the hydrogen is to clearly show you the carbon arrangement. So the iso unit, if you go back, rewind me a minute or two ago, I said was carbon, carbon, carbon. There's your L, right? There's the kink. That's what we're looking for in the ISO unit. So there's 3 in total. So here's my 4th, and there's my 5th. There you go. And now number 3 says, are there any other choices? Are there any other ways that you can draw pentane, 5 carbons, same number of hydrogens, and still draw it a different way with a different shape? Okay, well, let's try a couple of options. So we had 1, 2, 3, 4, right? And in the first case, I drew it on this second carbon in. Okay, so if that's what we want to do, then why not get rid of that there and draw it here? It's the same thing. There's no difference, folks. Why? Because look. 1, 2, 3, 4. There's the longest chain. And this carbon is the second one in. Down here, 1, 2, 3, 4. And this carbon is not the third one in. This carbon is still the second one in. That's its shortest. That's its shortest route. The only thing that I've done is that I've taken this structure and I've just kind of flipped it. I've went left-handed to right-handed with it. And when I flipped it, I'm kind of looking on the front side here, and here I'm looking on the back side of that molecule. So it's still the second carbon from the end. I have a carbon. And this one is the second carbon from an end, and I have a carbon. So these two are actually the same. There is no difference there. All right, so let's try another way. So let's say that we do 1, 2, 3, and maybe 1 here. There's 4, and maybe 1 here. That's 5. That's wrong as well. Why? Because look. Longest chain, continuous chain. 1, 2, 3, and 4. There you go. And this carbon is the second one from the end. Folks, this is 4 carbons, second one from an end. This is 4 carbons, second one from the end. So, this is actually the same as well. There's no difference in those either. You've just drawn it a little weird way on a sheet of paper. That's all that you've done. Okay, so what about another way? Let's do 1, 2, 3, 4, and maybe 5. Is that different? We've not had any luck so far, but is this one different? Ding, 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 ding. Yeah, it is. The longest chain that you can continuously get here is 3, not 4. Kind of ends. You have no other option. You got to stop. And here you've got a carbon hanging down from the bottom, and you got one hanging up from the top. You know, if you drew both of these down, it means the same thing. We like to draw them where they kind of are further apart. We don't like to condense or squeeze things onto a sheet of paper. We like for these atoms to spread out as much as possible. So I put symmetry into the molecule for that reason. If I draw one down, I draw one up just by nature. That's the way that the molecule will orient itself anyway. So I'm thinking like a molecule when I begin to draw these. So just make everything very roomy. That's the only thing that I'm telling you, okay? So 3 carbons in total, and I have one up here and one down here. So there is another option that we can draw pentane, and that is another isomer that pentane has. Now, this is not called isopentane. Now, you're again scratching your head and saying, well, why not? Because a name can only represent one structure. That's it, okay? A structure can have multiple names. Don't get me wrong. A structure can have multiple ways that we name it. But when I look at a name as a chemist, as someone working in a lab, that name should only represent one structure. That's it, no more. So for that reason, this is not called isopentane. We have to call this a different way. So once more, there's common names, and there's more of what we would call an IUPAC name. And that IUPAC name is going to be called a systematic name. So we're going to be focused on systematic names. They're actually encouraging us to leave the common names. So this ISO unit, they really don't like this anymore. They want us to get away from this. Don't be naming things common. The problem is that we have old school people that are still in a lab that still order, still talk the talk, and they still use the common nomenclature that they learned 30 years ago. And there's no way around it. We cannot leave it because those people are teaching new people the same nomenclature that they learned, maybe not as heavy, but they're still teaching it, just like I did with you. And that's because it's still used. Maybe not as much, but it's still used in a laboratory environment. All right, so now we're starting to see the murk and the mud of organic. All right, so here let me kind of wrap everything up. Number one, nomenclature is going to be a focus of this lecture and all the videos to follow. We're going to have to learn how to name. When we name these structures, well, we can name what we would call straight chain. Everything is lined up in a row. These are easy. That's kind of what we started off with. Meth, eth, prop, bute, and so forth. However, we also have isomers that can happen. And isomers are the same number of atoms all the way across the board. They just link up differently. And these isomers we're going to have to name as well. And there's two different ways that we can name these. There is a common way that we can name them, and then there's an IUPAC way that we can name them. And this IUPAC way is also called systemic. A systematic name, not systemic. A systematic name, S-Y-S-T-E-M-A-T-I-C. So we're going to have to get comfortable with all of these, right? And it's going to take some time and it's going to take some practice. And that's the only way that we can learn organic is if we do example after example after example after example. All right, so let me do another example for you. And this is going to be hexane. All right? So if someone asked you to draw hexane, you would give me 1, 2, 3, 4, 5, 6. Hex. There we go. Again, I'm leaving off the hydrogens. You know that they're there. You know that there's enough of them to get carbon all 4 bonds. So I'm just going to leave them off. That way we can focus on the main chain only. Otherwise, the diagrams and drawings are going to get pretty ugly. So we have this thing called isohexane. 1, 2, 3, 4, 5, 6. There you go. Well, isohexane is also this one. 1, 2, 3, 4, 5, right? And instead of the second one from this end, it could be the second one from that end. So there we go. I'm going to put a big or here. They mean the same thing. There's no difference in those two structures. Okay? And then I also have another version, another isomer of hexane. 1, 2, 3, 4, 5, and then I can put it smack dab in the middle, right there. So this is plausible. Same number of carbons, same number of hydrogens. I can't call it iso. The reason that I can't call it an iso unit is because this L represents the iso word. That's what I always want you to remember. That L shape there at the end, there's your iso. This one, yeah, it's an L shape, but it happens much further in. It's not the next carbon from the end, right? It needs to be here if that's what it wants to do. It's inward one more. So we can't use the word iso here. We have to name this a different way. Okay? But that's still not the only option. I could also draw another isomer. And that is 1, 2, 3, 4. And I can put one here, 5, and I can put one there, 6. Well, that also means 1, 2, 3, 4. If I drew one down, I could also draw one up. These two are the same thing. This doesn't matter. And then I can flip this backward the other way too. I can take this one to the left and point it up, and this one to the right and point it down. That's the same thing. There's no difference. So that is another isomer that we could bring into the picture. But it doesn't stop here. All right, so I'm going to have to block these out. There's one. There's another choice. There's a third choice. There's a fourth choice. And we also have a fifth. What is that fifth one? 1, 2, 3, 4, 5, 6. It can be on the same carbon. Or 1, 2, 3, 4, and we can just tackle the other end. 2 from the right-hand side, or the second one in from the left-hand side. Either one of these are the same molecule. It doesn't really matter. Now you see the problem. Okay? The further up we go, the more choices we're going to have. The more choices we're going to have, the more names we're going to have to learn. And this is why I'm telling you that common names are taking a back seat. We don't want to learn common names for all this crap. We want to learn a procedure, and a procedure that will name this the same way every single time if we can get away with it. And we want to do away with those common names whenever possible. Because if I can remember the rules to the game's not going to change. Unless they try to do something and cheat on me, which does happen in organic. So, each one of these has an IUPAC or systematic name, and they also have a common name. I'm not going to require you to give me both for every single structure that comes around. I want to make that clear. I'm going to focus on IUPAC whenever possible. But there are some names in the common nomenclature world that we have to get used to, and ISO is one of those. So you are going to see me use ISO quite often. This is something that's never going to leave us. It's something that's always going to be there. But I want you to keep in mind that all of these others are isomers as well. And all of those others also have common names that we can bring into the picture. But we're going to focus on IUPAC for the majority of them. But ISO is one of those that we can't necessarily get rid of every single time. Okay? So that's where I'm going to stop this video. In the next one, we're going to continue on. We're going to look at some of these other structural changes that could happen in these organic molecules. We're just going to talk about these things first, and then you're going to start to see me naming more and more and more and more. So in the next video, we'll talk about more structural changes of an organic alkane.